Yo, what's up, guys? Welcome back. Episode 69, I think. Yeah, episode 69. Wow, there we go. We got a bell sprout today, and we're gonna check out our sound, bell sprout sound. Let's check out the cry.
I've heard it countless times. It doesn't matter where you get your car loan, but it should. When I got
Put it up. 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 That's that sound right there. Nice, that's our Pokemon sound today. I got a Dunkin' coffee today, and they put 500 pounds of sugar in it. I was not expecting it. I feel like I'm drinking diabetes right now every time I take a sip of it, but, you know, I still paid for it, so I still got to drink it, but damn, there's a lot of sugar in that. Yeah. Anyway, let's take a look at our problem of the day, and then we're gonna do a few problems. Check out a few problems. Go drink some water. Minimum time to repair cars. Let's take a look. Let's maybe try and attempt this one. You're given an integer array of ranks representing the ranks of some mechanics. Ranks I is a rank of the ith mechanic. A mechanic with rank R can repair n cars in R times n squared minutes. Okay. You're also given an integer cars representing the total number of cars waiting in the garage to be repaired. Return the minimum time taken to repair all the cars. All mechanics can repair the cars simultaneously. Okay. So these are our mechanics here, right? The ranks. And each mechanic can repair a car in R times n squared minutes. So 4 times n squared minutes. What is the n in this case? I actually... squared minutes. Okay. So we have, in this case, we have 4 mechanics, right? So... I think I need to go blow my nose, dude. Dude. More binary search, bro. I'll be back in a second. I gotta blow my nose. You know, as what I said yesterday, I'm not very good with binary search, to be completely honest. But I guess we might as well try and solve this question. Take a look at the discussion. Coco, stop eating the bananas. Fast mechanic repaired 2 cars. The timer... It can be that cars cannot be repaired in less than 16 minutes. I'm trying to think here. 2, 4, 6, 10. So they get the amount of cars that they split among each of these people. They do binary search. But I don't know how to implement binary search on this. Looking at something per car. Let's see if Leetcode has a video on this. Minimum time to repair cars. He does have a video. Let's take a look.
Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem, minimum time to repair cars. And before we get into it, I feel obligated to mention the fact that the last few problems that we've solved on the channel are pretty heavily related to today's problem. So if you struggled with those, or if you didn't watch those videos or solve those problems, highly recommend it. But anyways, let's get into this problem, which is going to basically be the exact same binary search pattern, where instead of doing binary search on a data structure like an array, that's typically how we do binary search usually. Instead, this binary search pattern is to, rather than applying this to an array, we're going to apply this to a range, or sometimes I call it a search space, because that's the whole idea behind binary search. You're running binary search on some data, but the data doesn't have to be a data structure. It could be just some range of values, and that's what this pattern is going to be. It's going to involve a little math, so let's get into the problem description. The idea here is that we're given a bunch of ranks. And so in this example, I think we just have 4, 3, 2, 1. And we're also given a parameter cars, so that's just going to be a number. In this case, that is going to be 10. What the ranks represent is kind of the opposite of what you would expect. For example, they give us this equation here, and basically the entire problem centers around this equation. If you are decent at math, you should be able to simplify it pretty quickly. If not, it's a little bit tricky, so don't worry too much about it. So we have r times n squared. So what they say is that we're given a bunch of mechanics. So these numbers represent the ranks of every mechanic, which is basically like a person who's going to be fixing the cars. We need to fix 10 cars, and this equation tells us how quickly each mechanic is going to be able to fix those cars given the rank of that mechanic. So, and just to make it very, very clear, the higher the rank of a mechanic, the slower that they will work. So a high rank means they work slower. So this equation over here, let's over here on the left say the minute versus the number of cars that they can fix for any given mechanic. So what this equation represents, because it's very important to understand this part, this is probably where a lot of people are going to make mistakes, myself somewhat included. N is going to be the number of cars. So it's kind of the opposite of what you'd expect. You plug 1 in. So for the first mechanic, let's say I'm looking at this mechanic who has a rank of 4. So I can put 4 in for the R. For N here, how long is it going to take them to do 1 car? So for N, I want to do 1 initially. I'm going to put 1 in, so I'm going to do 1 squared, and that's just going to be 4 times 1. So that's 4. So what that means is that in 1 minute, I guess I'll put that over here on the left, the number of cars, we plugged 1 into the number of cars for N, and the number that we got out, 4. So that means it takes them 4 minutes to do 1 car. You can see even I'm kind of almost messing up here because it's so much like the opposite of what you would have expected. But anyways, to do 2 cars, how long will it take them? Well, let's just plug 2 in here. We get 2 squared times 4. You can see how this is just a constant. So we're going to have 4 times 4. It takes them 16 minutes to do 2 cars. And let's plug 3 in now. So 3 squared, that's going to be 9 times 4. We get 36. So it takes 36 minutes to do 3 cars. To make it very clear, this means that after a total of 36 minutes, they would get 3 cars in total. So in some ways, it's like they're slowing down as they go. Okay, so now we understand what this equation actually means. So now let's get into the binary search part of this solution. The first thing we're going to do is set up our search space. We're going to have the low and the upper bound. So once we have that, then we can start running binary search on this space. It's going to involve a brute force component to the problem. That part actually, in some ways, is the tricky part. It does involve a little bit of math. I'll try to explain it. But just setting up our range right now, it's usually safe to assume that 1 is good for the starting spot. I guess I should start with what this range actually represents. Remember, what we're trying to do is, given these mechanics and given 10 cars, we want to know how much total time is it going to take for us to do all 10 of the cars with these 4 mechanics, and this is the rank of each mechanic. Well, we know that since this is not a linear problem, it's going to take some effort for us to figure that out. We can't just calculate it in constant time. Actually, now that I think about it, I don't think it's the non-linear nature that causes this. I think it's mostly the fact that we have many different mechanics and each one of them has a somewhat different equation. But anyways, for the amount of time, like they're probably not going to be able to do it in less than 1 minute. I assume that a minute is our smallest unit that we're working with. So I think 1 is probably a safe number to put here for the lower bound. So let's do that. So 1
It's
here.
cold,
But what's
man.
the upper bound going to be? This is another tricky part. What is the maximum amount of time it could take for us to do all 10 cars? Well, again, it's non-linear. So it seems like it's not super straightforward, but think about it again for a second. What does this equation tell us? Given some number of cars, it tells us how much time it would take a given mechanic to do those cars. So we could actually do this. We could pick any mechanic, pick any of them. After we do that, we calculate the amount of time it would take for that mechanic, just that single mechanic, and how much time would it take them to do all 10 cars. And I can say that that is a good upper bound, because I know that either I just have a single person available in the first place, and then I can calculate how much time it would take that mechanic to do all of the cars, or I have multiple mechanics available to me, in which case that upper bound will never be exceeded, because if we have multiple mechanics, then the actual answer will be somewhere in between. Thus, I think it's a good upper bound to pick a single mechanic and just calculate how much time it would take them to do all 10 cars. Whether we pick the fastest one or the slowest one, it doesn't really matter. This is the slowest, this is the fastest. But either way, it wouldn't matter to us because all of them will be working at the same time. But we're just simulating if one of them were working to give us a decent upper bound. So for us to do that, we can just plug it into this equation. We know that for this mechanic, this guy over here with a rank of 4, if we want to do 10 cars, we can do 10 squared. So that's going to be 100. So I believe 400 would be a pretty good upper bound for the time here. So that's how I'm doing that. So now that we have our range set up, we have 100 and we have 400. I got that, by the way, just taking a rank and taking the cars, squaring that. And now I'm going to run binary search on this, and that's going to involve calculating the midway point, which in this iteration is going to be halfway. So I think 200 is good. And this 200 represents the time in this case. We want to know how much time would it take us to do all 10 cars. We want to know the minimum amount of time. So now what we want to know is this middle value good or not? Because if this middle value is good, then what we're going to do is start searching to the left of it, because we're trying to find the smallest time that will allow us to repair 10 cars. So if this is good, if I give this a green, then we start searching on the left. We can shift the right pointer, which right now would be at 400, and we can shift it to be mid -1. Otherwise, if this is not good, that means that 200 minutes is not enough time for us to repair all 10 cars, then we need even more time. So we would shift our left pointer from here to be mid plus 1 because we need even more time than 200. We're going to start searching on the other side of it. So that's going to be the general idea here. Now, this part involves a bit of math, I guess. How do we calculate the time? Or sorry, not calculate the time. How do we calculate the number of cars? So if I give you 200 minutes and these are the mechanics that we have, this is the rank of each of them, how do I know how much time it takes for them to repair cars? Well, that's just a matter of solving this equation here on the right side. I guess I'll go ahead and do it. So we're just going to solve for n because we know n represents the number of cars. So we can divide both sides by r. We get the rank over here. I guess I'll spell it out this time. And then we just have n squared here. We can just square root this side, and then we are good. Now, what does this represent? It should tell us the number of cars we can do in this much time. So this will be plugged in over here, and then the rank we have to take individually because every individual mechanic is going to be able to do a different amount. So we're going to have to basically calculate this equation n times, well, in this case, n means the number of mechanics. So for every mechanic, we have to calculate this equation. And then we sum all of those up, and that sum will tell us how many cars we can do in 200 minutes if that sum is meeting.
I would have never thought about this. This is actually... I mean, to be honest, like, I don't really have enough knowledge about binary search in order to be able to, like, think like this, but like, I would have never, at least to this point of my career, like, trying to do these problems, I would have never thought about this. Like,
this threshold, then we're good. Otherwise, we are not good, and we will have to update our binary search accordingly. So that's the whole idea here. In this problem, I think 200 is going to be obviously good, because I think, just to do one quick iteration of this, the first mechanic is going to be square root of time, which is 200 divided by 4. And then the next mechanic is going to be 200 divided by 3, etc., etc. I think one of these terms is probably bigger than 10. Since this is good, we will then shift our right pointer here. So our next range would be something like this, 1 and 199, because now we're looking for smaller numbers than 200. Is there a time even smaller than 200, which will allow us to do all 10 cars? I think there probably is. I think 100 is going to work. And then we're going to get down to 50. 50 is going to work as well. And then eventually, I think we're going to go down, like, our range should be something like this, 1 to 25. And then I think the solution to this first example should be, I think 16 minutes should be enough for them to do all 10 cars. So that's the main idea behind this problem and this solution. I think the time complexity is going to be n, where n is the number of mechanics that we're given. And then log, the right number that we had was something like this, where we had the rank multiplied by the number of cars squared. So I don't know how to do that. I guess I'll just do r times c squared. And the rank is just any rank from the input. But anyways, I think this is probably precise enough. Okay, so just doing the initial setup, we have our left and right pointer. I will initialize it to 1.
Oh my gosh, dude. Okay, let's do our left pointer as 1. Our right pointer can be the max of our ranks. I know we can pick any one, but I don't know. So whatever. So while our left is less than or equal to our right, we want to calculate our midpoint, right? And our mid is right plus left minus left over 2. I think something like that. Oh man, it's cold in my apartment, dude. Calculate our mid. I guess in this case, this is our time, right? And then ooh, what's our formula here? Oh, our n is equal to, in this case, the square root of I think it's mid over rank. This is Python 3. I think we need the double. I'm not really sure how to do this part in terms of binary search. Oh my god, my ears, man. I know we're probably gonna need to do like, let's Java, some sort of like for loop here, right? Do if mid plus 1. Sorry, if and then we can just turn out n, I think. Else if mid is greater than what's that noise, bro? We could do like if mid is less than because we're gonna add n is technically gonna be sum, so if we do if n is less than mid, right, then we have to move our mid pointer to mid is equal to mid minus 1. Else if n is greater than mid, then our mid is going to be mid plus 1. I think else we just return n, right? I think. Let's take a look at what he does.
Solution to this first example should be, I think, 16 minutes should be enough for them to do all 10 cars. So that's the main idea behind this problem and this solution. I think the time complexity is set up. We have our left and right point rank. So ranks at index 0. Multiply it by cars squared. So cars times cars. Again, this is just filling in the equation that they gave us. So this is...
Oh, yeah. I didn't see that. Let's do the same thing as him. So we initialize to the first value, and then we do times. What is it? Yeah, cars times cars.
The amount of time it would take one mechanic to do all of the cars, and now we can run binary search within this range. I'll just initialize my result to some random value. In this case, it doesn't really matter how we do this, so I'll just do it like this. And then while the pointers have not crossed each other, for me, this is kind of just muscle memory. Calculating the midway point, we don't really care about overflow, so we just do left plus right divided by 2. I'm going to have a helper function, I guess. We don't really need to, but I will anyway, to give me the repaired count. So I guess I'll just call it count repaired. So we'll pass in a function, passing in the time. In this case, m is the time that we have. How many cars can we repair in that amount of time? If the repaired count is greater than or equal to the threshold, which is just the total number of cars that we're given, if that's the case, that's good. We can update our result to this time. Then we can shift our right pointer so that the time can be less than this. Otherwise, we'll do the opposite. We did not find a satisfactory time, so we need to increase the threshold. We need to set our left pointer to be mid plus 1 so that we can look for bigger values. We're guaranteed that this condition will execute at least once, so this will execute. And I think I saw a comment on the previous video where people said, well, how do you know that this will actually work on the last iteration? It's kind of a proof by contradiction. I think I've talked about it before in some videos, but think about this. If I have like some numbers like this, eventually we're going to get to a point where we only have 1 or 2 values remaining. So if this was my array, eventually we'll get to a point where we only have 2 values remaining. If I had set my right pointer to mid minus 1, then I basically said that, well, the mid result that we had was valid, but now we're looking for other valid results that are even smaller than the one that we saw. Either we will find one, there will be one that's smaller and valid, or we will not find anything that is smaller and also valid, in which case this will keep executing, and thus the result will never be updated. So it does work if you think about it and you run it on a few examples. It'll work on every single edge case, and that's because it has to work. It's like a mathematical thing that you can prove. Now, finally, to fill in this last function, I think you can probably do it on your own if you try, but I'll go ahead and do it now. Count repaired. We're given a parameter. I'll call it time. We want to know how many we can repair in this time. I guess I'll have a variable. I'll call it count for that. We'll return the count. And for us to calculate it, we go through every rank in the input. And that equation I was talking about, which, to be honest, I don't remember off the top of my head. Looking at the drawing, it said we have the square root of time divided by the rank. So I'm doing integer division here with the double slashes. So this will turn into an integer, and I don't think that's even necessary. I think it did work when I had that, but I don't think that that's necessary. We can just take the square root and then convert that into an integer and then add that to the result. So we will have summed the contribution of every single mechanic. We know the total number of cars we can do, and we will return that down here. And of course, I forgot the S, so the typo. And I also called this result when it should be count. Bad habit. But now you can see that this code does indeed work, and it is pretty efficient. If you found this helpful, check out Leetcode.io for a lot more. Thank
Okay. Calculate our mid. We need a helper function here, so count cars equal to, oh man, I'm gonna seize, bro. Oh my god. Let's just do the same. Head is equal to count cars. We pass it midpoint. Create def count cars. Passing in our mid. Create a count here, and we loop through for I in ranks. Did we find ranks? We do the count plus or equal to the square root of shit, what was the formula, dude? I don't remember. Time over R. Time over R, or I in our case. And then we just want to return our count. Here we got our cars, vol left is less than right, calculate our mid, we got our repaired. How we do this part? Well, if our repaired is less than our mid, then if our repaired is greater than or equal to, okay, we'll do the same as him. If our repaired is greater than or equal to our mid, What is cars in this case? If repaired. Why are we looking at cars? It's greater.
Count, so I guess I'll just call it count repaired. So we'll pass in a function, passing in the time. In this case, m is the time that we have. How many cars can we repair in that amount of time? If the repaired count is greater than or equal to the threshold, which is just the total number of cars that we're given, if that's the case, that's good. We can update our result to this time. Then we can shift our right pointer so that the time can be less than this. So that we can increase the threshold, we need to set our time can be less than this. Otherwise, we'll do the opposite. We did not find a satisfactory time, so we need to increase the threshold. We need to set our left pointer to be mid plus 1 so that we can look for bigger values. We're guaranteed that this condition will execute at least once, so this will execute. I think I saw a comment on the previous video where people said, well, how do you know that this will actually work on the last iteration? It's kind of a proof by contradiction. I think I've talked about it before in some videos.
Proof by contradiction. Why is this not running? I'm not sure. Oh yeah, we've got to cast this into an integer. Man, what am I doing wrong here, bro? Like, left plus right over 2. Repair is equal to count cars repair, yeah. Bro, I don't know why this is not working. Incorrect upper bound, bro. I don't. Oh, I think this is my issue here. Let's check out a test case just to solidify the knowledge. I kind of understand what's going on. I just get confused with the way binary search works, man. That's the issue. Like, and total cars repaired. Right is equal to 200. Right is equal. Our mid is 50. Interesting. Interesting problem. That was a good problem. I definitely need to keep working on binary search, man. Like, it's one I definitely really struggle with. Let's take a look at take a look at a binary search problem. I mean, sorry, a tree problem. Given the root of a binary tree, return the sum of values of nodes with an even value grandparent. If there are no nodes with even value grandparent, return 0. Okay. So we got an even value grandparent, right? So we go 2 plus 7 plus 1, 3. 5 is even valued. Okay. I think this would be a BFS problem. I think, personally. We start with our root. We'd add the children. Right? We save the grandparent after each iteration. So we would start here, go here, make the parent equal to this node, and then pass its children. Right? Add its children, and make the grandparent equal to that, and the parent equal to that. Do its children. And just keep adding the grandparent, I think. Okay. Input DQ, right? We're gonna create a queue. So Q is equal to DQ. We're gonna put root, parent, and grandparent. Well, I guess we're gonna pass in none for these ones, right? None, none. I'm gonna create a res value to store everything. While queue. Length is equal to the length of queue, right? And we're gonna do a for loop. So for it's called for I in range length. We do q dot pop left. Okay, so I guess node parent grandparent is equal to q dot pop left. Okay, so we do that. So we would do, well, if node dot left, right, we do q dot append current root, which would be node dot left, right, and then we'd append the parent, which would be the node, right, and then yeah, so we'd append the new node, we'd make the current node equal to parent, and then the parent of that node equal to the parent. Then we do if node dot right, we do the same, where we'd append the queue, we'd append the right node, append that, then the parent, right? And then inside the for loop here, we need to check, well, check grandparent is even, right? So if grandparent dot val is modulus 0, modulus 2 is equal to 0, then node dot val, then res plus or equal to node dot val. We just want to return our res. I think this is the way to do it. Is this how you check? See if this runs, bro. Cannot unpack non-iterable tree node. Why is this non-iterable? I added my values here, bro. Why? What am I doing wrong here? I think I gotta add an extra thing to make it a tuple. Has no attribute val. Okay. If not root, return 0. No attribute val. Grandparent.val %2 is equal to 0. Okay. Then res plus or equal to the node.val. How can I think we can do and bro, how do I check for jeez, man. There we go. I think this should work. There we go. Our intuition was right. BFS. Nice. Okay. Good job. I'm gonna quickly go to the bathroom and I'll be back. I'll be back in a second. All right, I'm back. Let's take a look at some other solutions. Online recursive solution. Yeah, they use DFS. Root dad, grandparent, if not root. Yeah, I mean, you can do DFS with BFS. 2 solution of Python. Not your pro. What is this? This is a, what are they using here? Stack? Yeah. What's this BFS? Whoops. I don't know. I think my solution is pretty readable. I mean, bro, we just create a queue, get the length, add each thing, check with the grandparent. Geez, what is this solution? If not root return 0. If root.val %2 is equal to 0, if root.left and root.left.left. Soft. If root.left and root.left.left. Oh, okay, right. So he's running through this at if we're the grandparent. Right, so if we're the grandparent and we have a root.left and then we have a root.left.left, then we add the root there and we keep going and then we recursively run through the tree. That's an interesting way to do it too. I mean, so many other ways you can do it. Oh. All right. Let's jump into like a assembly code 75 problems. I find this one really tough, but I have to come back to it in the future. Let's maybe do these 2.0s, finish the sliding window or something. Prefix hash map. Let's check this one. When do we do this one? Back in December. Is a subsequence. Give it 2 strings, S and T, return true if it is a subsequence or T false otherwise. Subsequence of a string is a use string that is formed for the original string by deleting sub. Okay. Okay, that give two streaks S of t, return true if S is a subsequence of T or false otherwise. So it's true because we have an A, B, C here. Okay. I'm thinking, do we just sort this T and just return if... Yeah, so I'm thinking maybe we make S hash t is equal to... No, maybe not. T list is equal to the list of T. And then we want to do T dot sort. Let's print T. T list dot sort. Sorry, T list. This is a... I wonder if this works. I'm just curious. No, okay. Let's just do it the normal way. So give it two strings S and T. Return true of a subsequence of T. Well, how are we gonna do this? Well. It's tagged as a 2-pointer. How can we use 2 pointers to do this? I don't know. Can we make a pointer here and then a pointer here, loop through this with a for loop? Then check, well... height is equal to... My thought process here is to use a left pointer over here. We make left is equal to 0. My thought process is, I don't know if this would work, but we make 2 pointers, right? Left is equal to 0 here, right? Then we create another pointer in this while loop that loops through this, right? So we keep looping. Then if left 0 is equal to right 0 or whatever, we we put this back to 0, so we start from the beginning, and we loop through again and check if B is here. And we loop through again, and if it's not there, then we automatically return false. That's what I'm thinking, but maybe there's a better way to do it. Maybe I don't know, maybe we can make 2 hash maps too, so maybe S map, T map. Can you do this with a string? I don't know, like let's print S map, print T map. Okay, maybe we don't even need an S map. We can make a T map, right? And then do, well, for I in S, if T map if I if SI not in T map, we can return false. Otherwise, we just return true. Is this equal to list S? Dude, I feel sick after drinking that coffee, that amount of sugar, bro. S list I in T map. Dot string. List indices must be integers, the slice is not a string. If S list I don't think. List indices must be integers or slices, not string. Believes something can be none of the characters without disturbing the relative position of the remaining characters. Ace is a subsequence of okay. So we're maintaining the relative positions of the remaining characters. Okay. Well, that makes it a little different then. Okay. This won't work. Okay, I didn't really think about that. Okay. We're gonna need a while here. Okay, we're gonna need a... We're gonna need a... Let's do 1 is equal to 0. 2 is equal to... Two is equal to 0. We need a cutoff. Oh, let's do, well, count is equal to the length of t minus 1. Okay, let's do while 2 is less than or equal to the count. If list of t, if s list 0, okay, if s list 1 equal to t list 2, then 1 plus or equal to 1 every time we increment 2 plus or equal to 1. And we reset the count. 2 is equal to 0. It's probably such a stupid way to do it, but maybe we create a found variable and we can be like, well, return true if found equal to the length of s, else false. Equal. No, this is not the way to do it. For right in t. If Let's do like a count here. Then we increment our count. Count plus equal to 1. Bruh. Oh, sorry, that's left. Whoops. Got the increment left. Whoops. Oh, there we go. Did I just do it? Nope. I didn't. Out of range. Why are we out of range here, dude? Oh. String index is out of range. Two out of 21 test cases passed. Like, bro, what? Okay. Bro, alright. Is it return? Bro, what are these edge cases, bro? Like, what the fuck? Like, bro, I don't know. Generally, I don't know what's wrong with my stuff. Oh, dude, that's what I forgot. I have to check if s left is equal to the length of s. Let me just return true, right? Oh my gosh, dude. Sorry. If check left, not what the actual value is, equal to the length of s. There we go. That was my edge case, bro. There we go. Okay. Is this a binary search problem as well, bro? No way. Alright, let's go to something else. Subsequence. Max number of case-on pairs. I don't know. I think I solved this one recently, actually. February 7th. Yeah, it's about a month ago. Okay, I don't know why this is here, but let's get rid of that. Given an integer array nums and an integer k. In one operation, you pick two numbers from the array whose sum equals k and remove them from the array. Return the maximum number of operations you can perform in the array. Okay. I think we create a count. I think we create a left pointer here and our right pointer is at the end of the array. -1. I said while left is less than or equal to right. Would we sort them though? I don't know. Would we sort them? I don't know. I don't know if we'd sort this array, but I'm thinking maybe we can. If we sort it, I'm thinking we sort it. We sort our array, we create a count, we create our left and right pointers. We move through while left is less than right. If nums left plus nums right is equal to k, then we just want to... Dude, how do we... Dude, I feel so weird right now in Python. I think we have a remove function, so we do nums up remove, nums left, nums up remove. Do we actually have to remove though? Or can we just... I guess left plus or equal to 1, right minus or equal to 1, and we can just increase our count. I don't think we technically need to remove. We just return our count. Okay, we got an infinite loop. Okay, we have an infinite loop because we're not actually looping at all, so... If nums left plus nums right is equal to k. Okay, let's run through this test case. If nums left is equal to nums right, we delete these two, right? And we create what our length of our array is 2. Okay, maybe we just increment our count, right? But then we leave these outside. Dude, why do I feel so weird, bro? Like, ugh. Okay, because we have another 3 and a 3. Right. Okay. But when we have duplicates, can we pass this into a set? Hashy, to get rid of the duplicates, hashy is equal to set nums.sort. Instead of nums, we call this hashy. I call this one hashy. Curious, will that work? Get rid of our duplicates. Object is not iterable. What? Okay, what if we just do nums dot sort? We just pass in our nums here. Is that the reason why it's not iterable, or is the hashy not iterable? It's not subscriptable. Okay, this is crazy, but what if we pass in the set nums, right? And then we make so we get rid of the duplicates, and then we make nums is equal to hashy, and then we do nums dot sort. Is that crazy, bro? Or is that like 200 million IQ? I don't even know if this will work, but I'm just curious to see. Like, maybe this is a little crazy, but there's no attribute sort. I think we have to pass it back into a list, and then we sort it. Oh, that didn't work. Well, actually, maybe we will need the duplicates. Maybe that's not the best way to go about it. Okay. So maybe we actually have to delete the values, like thumbs up remove left, thumbs up remove right. Let's see what this gives us. This index is out of range. Thumbs up remove. Do we maybe need to reset? We could. Maybe we make our left equal to 0 and then our right equal to the length of nums minus 1 again. And then we restart searching and we keep making it smaller and smaller and smaller. Would that fix it? Now this index is still out of range. Okay. X non-list. Nubs left. Okay. So I was kind of right at first where we increase our left. Right, minus equal to 1, right? But then instead of resetting it here, right, we need to check, well, this is what I was kind of thinking about before, else if, if nums left less than or equal to nums right. Sorry, if nums left plus nums right is nums right less than or equal to k, we need a bigger value, so we increase our left, right? Else, if it's greater than k, then we need a smaller value, so we do right minus equal to 1, and we return our count. Okay. What am I doing wrong here? Six. Bro, I don't know why I'm not feeling good right now. Ugh. Wow, why are we checking equal here? It should be less than. Because if they're equal, then we want to run this one, not the other one. Okay, then we go inside here. 1 and 4. Well, if 1 and 4 is 5, so if 5 is less than 6, it's 5 is less than 6, then we want to increment right. We want more. Well, remove 1. How is this 2 here? Well, we got 3 and 3. How is this 2 here? Oh, output is 2. Okay. So we got 3 and 3 here. We increment right here. We increment our left here. We check 1 and 4 is 5. How does this equal 2? I don't understand. Like, that was our issue. Okay. Okay, well, if our left and our left, let's think about this. If our left 1 and 4 is 5, right? Our 5 is less than k. We need a bigger value, right? So we, oh wait, no, this is, okay. Let's kind of try and visualize this better because we have a sorted array. So if our sorted array is 1, 3, 3. Oh, we got 3 3s. Okay, yeah, and then we have a 4, right? One plus 4 is 5, right? So if 5 is less than k, we increment, we need a bigger value. So then we check, well, we go to 3 and 4, right? That's 7. So it's greater than k, so we move here, right? So now we're at 3 and 3. Okay. Well, 3 and 3 is 6. So we increment to 1, right? And we increase both, right? So it goes here, this one goes here, this one goes here. Oh, okay, it runs one more time because it's equal, right? But instead we need less than, but they're equal, so we will run it one more time. In this case, it's just 1. So Okay, nice. Cool. Done now, 2 pointers. Let's check out like let's do this problem. And then we'll call it. Jeez, okay. Two strings are considered close if you can obtain one from the other using the following operation. Operation 1, swap any two existing characters, for example, A, B, C, D, E. What do you mean is close? Two strings are close, they contain one from the other using CV. In two operations. Word 1 is Kaba. I don't think, see, with this problem here is that I don't think we need to, I don't think we need to use all the different operations here. Like, I don't think we specifically need to like recreate these operations, but I think there's probably a trick to it where we can just kind of look at the string and return if it's possible or not. Like, I feel like if the word has the same amount of values, then we can keep swapping them and it'll work and transfer every occurrence of one existing character into another existing character. Right? So I think really all we need to do is just check the length and check the values. I don't know if that's crazy. I think that's the way to go about it. I think if word 1, we have word 2, and we just have to, I think that'll work, but you know, I'm not really 100% sure, but let me respond to this text really quick. Okay. So I think that's what I'm going to do, right? So let's try this out. So let's go word 1 map is equal to counter word 1, and we can do word 2 map is equal to the counter of word 2. For key, sorry, for, I guess we can do key value in hang on, let's just print word 1 map. We print word 2 map. Jeez, man, I'm really not feeling good right now. Got the U encounter. Okay, so we got ABC, we got BCVA. Because you can see here, really, we return false here. I mean, they're not the same, right? ABC has the same here, right? You can see. In case 3, we got 3, 2, and 1. Right, so technically we need to check the length of the keys. Because if the length of the keys are the same, then we're good. How can we check that? Oh. We can do, I'm thinking, for key value in word1 map dot items, key if value not in world1 map we can just instantly return false, right? Otherwise we return true. If value or key not in word Am I checking this properly? I don't know. I mean, this seems a little bit too simple for a medium level problem. 57. My intuition is to check if the value is in the hash map. Is to create 2 separate hash maps for word 1 and word 2. Then check if the value is in both of hash maps, and the key is as well. If not, return false. Is this the correct way to think about the problem? Two strings considered close if they meet both conditions. Same set of unique calculator. Okay, I had the right intuition. Okay, I had the right intuition, so I had the right thought process here, but I didn't really execute it well with the code, right? So if the length of word 1 does not equal the length of word 2, then we can return false, obviously, right? We create our counters, right? So the proper way to check the keys here is to do, well, if I didn't think about this, if set world1 map dot keys does not equal set word2 map dot keys, we return false. Now to check the values, we do, well, yeah, it's sorted. Okay, if sorted world1 map dot values does not equal sorted world2 map dot values, right, then we, oh my god, I'm thinking Java, bro. No Java, dude. Then we would just return false, right? Otherwise we just return true. I think we can get rid of these print statements as well. So I had the right intuition, but I just didn't execute it the way. Object is not iterable. Oh, whoops, I'm not calling the function. There we go. Now there's probably, I'm sure there's probably a faster way to do this. Okay. Yeah, pretty much same thing. I mean, that's an interesting problem. This is probably an easier problem, but okay. All right, guys, I'm gonna call it there. Thank you guys for watching. We'll do some more problems tomorrow. See you guys later.